Before I even started making videos here on YouTube, I was always most fascinated by organic chemistry, and this was often to the point that anytime I learned about a new compound, I was immediately excited about the idea of trying to make it myself. However, as time went by, it became increasingly obvious that not having any nitrite salts was an enormous handicap. Sadly, nitrite salts aren't something you can readily buy, at least here in the US, which I'll discuss more in a minute. Since one of my main goals in the work I do here on YouTube is to try and get all of my chemicals from ordinary retail stores, I decided I had to try and figure out how to make this chemical myself. On that note, today I'm going to demonstrate several ways to make the extremely important chemical potassium nitrite. As a quick disclaimer, in case YouTube tries to take this video down, I said I'm making potassium nitrite with an ITE ending, which is a completely different chemical than potassium nitrate, and cannot be used to make gunpowder or any related energetic mixture. YouTube seems to have developed a rather strict policy on nitrates lately, so I just want to make it exceedingly clear that this compound is entirely different. Now, to get started making potassium nitrite, I began with a 5-pound bag of potassium nitrate, which I bought on Amazon for $12. Potassium nitrate is a binary salt of potassium and the polyatomic anion nitrate, which has the formula NO3. My plan is to basically take one of these 3 oxygen atoms away from nitrate to reduce it to NO2, which is nitrite. This might sound simple, but I spent 6 months working on this project and trimmed this video down from 9 hours of footage. Now, there's several reasons why making nitrate into nitrite is so difficult. For one, nitrate usually prefers to decompose completely under reducing conditions rather than to simply give up one oxygen. Also, even if you're able to pull off a single oxygen, it's nearly impossible to do so uniformly, and since nitrite salts tend to have similar solubilities as nitrate salts, purifying crude samples is a nightmarish ordeal. If you're truly an insane person, you could always just make a nitrogen monoxide generator and feed it into potassium hydroxide, but that's basically 10 times the work, only to arrive at the same nightmare purification. So at this point you might be asking, why bother going through all this trouble? And the reason is that nitrite salts are now nearly impossible to buy in the United States. This is because consuming even small quantities of nitrite salts will rapidly oxidize the iron in hemoglobin from the +2 to the +3 state. This ferric form of hemoglobin is unable to bind to oxygen, and so the victim of nitrite poisoning is quickly suffocated while still fully able to breathe. If caught early enough, methylene blue is an effective antidote for nitrite poisoning as it quickly works to reduce the iron in hemoglobin back to the +2 state. But otherwise, the poisoning is quite consistently lethal. For this reason, I do my best to not eat this salt, but it seems enough people had the opposite idea that a federal ban was established for online sale of the chemical. This is honestly a tragedy because nitrite is nearly indispensable in the lab. For example, nitrite is required for diatorization reactions which have vast application in organic synthesis, particularly in the preparation of azo dyes, aryl halides, and alkyl nitrites, as well as a wide array of other chemicals. Nitrite is also used extensively in meat curing due to its ability to inhibit bacterial growth, accelerate the curing process, and give the meat a nice pink color rather than a less attractive grayish-brown color that cured meat would otherwise have without nitrite. Nitrite also has an extremely powerful vasodilating and hypotensive effect when consumed. This effect is more passive when consuming foods high in nitrite and results in an overall lower blood pressure, meaning less strain on the heart. In fact, some researchers theorize that the high levels of nitrite in certain foods is one of the main reasons that the Mediterranean diet is linked to a longer life expectancy in a world where heart disease is one of the biggest killers. This vasodilating effect of nitrite is also used extensively in medicine, with organic nitrite such as amyl nitrite being a classical treatment for acute hypertensive episodes, as well as an effective treatment for cyanide poisoning. Now, generally speaking, reducing nitrate to nitrite is done by heating a nitrate salt to its melting point in the presence of a reducing agent. Many different reducing agents are possible, with each one offering unique benefits and drawbacks. This is a very basic procedure that I've seen or read about being done in a huge variety of ways, and I even did it myself with pretty good results once before on this channel. For this video though, I decided to try 7 different reducing agents so I could directly compare their results. For a quantitative comparison, I first decided to run all of my tests very simply at a test tube scale to both get an idea of the practicality of these procedures under easily accessible conditions, and to get a direct comparison of percent yield under conditions that were easier to tightly control and replicate. I then decided to redo the procedures that seemed most promising at a bulk scale to see how the methods compared when trying to produce an actual usable final product. On that note, to get started, the first thing I tried was the reduction of potassium nitrate using lead. This idea is from Wikipedia, and it's the method I've always heard most commonly cited for making nitrites from nitrates. I decided for this batch, along with all of my test tube scale batches, to use 4 grams or 0.04 moles of potassium nitrate and a stoichiometric equivalent of each reducing agent. For metallic lead, this came out to 8.27 grams. And these two chemicals were poured directly into a test tube and heated over a Bunsen burner for 12 minutes. The idea here is that potassium nitrate melts at 334 degrees Celsius, at which point it will begin to react with the lead and oxidize it to lead oxide. At the same time, potassium nitrate will lose an oxygen and be reduced to our product, potassium nitrite. This first reaction with elemental lead was actually quite visually interesting compared to many of the other reactions I tried. It produced a good deal of bubbling, along with a very obvious production of yellow and red lead oxides. This was really promising to me at the time, as it showed that a reaction was indeed happening. Anyway, after 12 minutes, I decided to stop the reaction and allow the test tube to cool down. This reaction probably could have been continued longer, but in the interest of keeping the reaction conditions the same for all of these preliminary trials, I cut the heat anyway. At this point, I moved on to my second trial using another 4 grams of potassium nitrate along with 2.23 grams of reduced iron powder for my reducing agent. This idea came from Wikipedia as well, and the idea is virtually identical to using lead, only dramatically less toxic. This one wasn't quite as visually interesting as the lead reduction, although I did see the iron powder blacken along with traces of a deep orange, which told me that the reaction was likely also working as intended. I also noted that once the bubbling had stopped, the clear layer of molten potassium nitrate had yellowed significantly. This is due to dissolved nitrogen oxides and a pretty good confirmation that nitrite had indeed formed. I allowed these two to continue reacting for the allotted 12 minutes, took the tube off the heat, and then moved on to my third trial using zinc powder. I kinda came up with this one myself, figuring that zinc was a better reducing agent than iron, so maybe it would work. For this one, I used 2.61 grams of zinc for the 4 grams of potassium nitrate. And in all honesty, this one was the least visually interesting of all my metal reducing agents. Upon applying heat, the mixture bubbled more than iron, but less than lead. And the resulting molten salt layer had a definite yellow tint to it as with iron, but it was distinctly more faint. This was again taken off the heat after 12 minutes and allowed to cool, and at this point I decided to move on to some non-metal reducing agents, starting with calcium sulfite. This is the reducing agent I used when I made sodium nitrite in the past, and when it comes to non-metallic reducing agents, you're actually fairly limited in what you can use to reduce nitrate. Reducing agents used in this process must either be insoluble themselves or form an insoluble salt during their reaction with nitrate. This is critically important because it means that they can subsequently be removed from the crude nitrite by filtration. Anyway, for this test, I ground together 4 grams of potassium nitrate with 4.8 grams of calcium sulfite and loaded it into a test tube. Since this specific mixture really couldn't form a molten mixture like the metals did, I moved to instead using a blowtorch to try and heat the tube as evenly as I could, while still maintaining the 12-minute time limit. Now, the idea with this reaction is that sulfite is a pretty good reducing agent, and should react with nitrate forming sulfate along with the target nitrite. The byproduct calcium sulfate is basically insoluble and pretty easy to remove by filtration. After this was done, I set it aside and repeated the process with 4 grams of potassium nitrate and 5.12 grams of calcium oxalate. I think I also came up with the idea for this one myself, and the reaction here looked nearly identical to the previous one. Now, the idea with calcium oxalate is that the oxalate anion is a hydrocarbon that decomposes at relatively low temperatures to form carbon dioxide, carbon monoxide, and carbonate. Ideally, though, it would instead be oxidized by nitrate, forming exclusively carbon dioxide and carbonate as byproducts. The carbon dioxide would float away as a gas, while the insoluble calcium carbonate could be easily filtered away. With trial number 5 out of the way, I went ahead and moved on to trial number 6, and for this reducing agent, I decided to try ferrous oxalate. This is another oxalate salt, and I got this idea from a Science Madness forum. Like before, I weighed out another 4 grams of potassium nitrate, and this time 5.76 grams of ferrous oxalate. I then ground them together in a mortar, transferred them to a test tube, and began to heat. The idea here is that when heated, yellow ferrous oxalate will decompose to form carbon dioxide, carbon monoxide, iron oxide, and some metallic iron. The iron formed this way is pyrophoric, and will ideally be quickly oxidized by the nitrate to form nitrite along with additional iron oxide. This one actually did look pretty cool, with the yellow oxalate decomposing to black and then red iron oxides as the reaction proceeded. This was again held for 12 minutes, taken off the heat, and now it was time to move on to my 7th and final method, which is a bit of an outlier from the rest. For my final method, I decided to try reducing potassium nitrate using calcium formate, which is an idea I took from the channel Experimental Chemistry. The idea here is similar to using calcium oxalate, except that formate is a better reducing agent than oxalate, but also very soluble. To this end, the method he outlined in his video, downscaled to match my other trials, began by dissolving 3.28 grams of calcium nitrate in distilled water. To this was added 2.76 grams of potassium carbonate dissolved in a minimal volume of water, which immediately reacted, forming potassium nitrate and insoluble calcium carbonate. The final step was to add formic acid slowly until all of the calcium carbonate dissolved, which left me with a solution containing calcium formate and potassium nitrate. This was next boiled down until a salt had formed, and this still somewhat wet salt was finally transferred to a test tube to begin the 7th and final run of heating. Now, something about this reaction that I don't recall from his video is that this mixture doesn't seem to do much when heated, until it reaches a very specific temperature, at which point it reacts violently. This produced a massive amount of vapor and was violent enough that it could be a genuine hazard at a bigger scale. I didn't mind this too much though, because to me this was a clear indicator that the reaction was a success. And for this one trial, I didn't go the full 12 minutes because it felt clear to me that the reactants were all certainly used up during the violent decomposition. Anyway, at this point, all of my initial trials were done, and now I had to clean them up so that I could compare the performance of each reducing agent. For this, I began by adding distilled water to each one of the test tubes to begin to try and dissolve these fused masses of salt. This process was fairly quick for tubes 4 through 7 and worked really well, but the first 3 turned out to be quite a pain. The main reason for this is that the salt masses obtained by using metal reducing agents had very low volume and thus very little surface area to help speed up the dissolving process. Not only this, but the fused masses also expanded as they cooled down, which broke all of the test tubes they were in. However, I did eventually get all of them to dissolve, at which point I passed them each through vacuum filtration to remove the insoluble solids. For trials 1 through 3, these insoluble solids were mostly unreacted metal powder along with their divalent oxides. Lead oxide in particular is very toxic, so this step in particular needs to be handled very carefully. For sample 4, the insoluble solid was calcium sulfate. Sample 5 was calcium carbonate. Sample 6 was ferric oxide, and sample 7 was also calcium carbonate. Each one of the resulting filtrates was next diluted to 50 milliliters, transferred to centrifuge tubes, and set aside. Now, to actually test how each one performed, I decided to do a series of titrations using potassium permanganate. The idea here is that under acidic conditions, permanganate will oxidize nitrite to nitrate, while itself being reduced first to manganese dioxide, and then to soluble manganese 2 ions if the conditions are sufficiently acidic. Since permanganate is an extremely deep purple color while divalent manganese is basically colorless, the change in color from purple to clear or vice versa will mark the endpoint of the titration. In order to determine how strong to make my permanganate titrant, I figured that none of the samples did worse than a 15% conversion of nitrate to nitrite. If they did do worse than 15%, then the method was basically useless to me anyway, so I didn't really care to know exactly how badly they did. If I began with 0.04 moles of potassium nitrate every time, then a 15% efficiency would correspond to 0.006 moles of potassium nitrite produced, which would react with 0.0024 moles, or 0.379 grams of potassium permanganate, in the presence of 0.0036 moles of sulfuric acid. With this in mind, I decided to make a 0.024 molar solution of potassium permanganate by adding 3.792 grams of potassium permanganate and 10 grams of sulfuric acid to a liter of distilled water. Sulfuric acid was used in excess here as nitrite solutions tend to be quite alkaline. At this concentration, it would take all 50 milliliters of my nitrite sample to completely react with 100 milliliters of the permanganate solution, assuming a 15% conversion efficiency. If the efficiency was higher, it would take less. With this rather unintuitive setup, I decided to use the potassium nitrite analyte as my titrant, and the permanganate solution of known concentration as my titrant. This titration is the reverse of a typical setup, and done partly because potassium nitrite will decompose under acidic conditions and so must stay alkaline up to the point that it reacts with the permanganate. Anyway, with all that out of the way, I first standardized my crudely made permanganate solution against a 0.6 molar solution of reagent-grade potassium nitrite. I ran this twice before running my analytical samples, and then once again at the very end in order to test whether any of my permanganate had decomposed throughout the process, as it tends to do so when acidified. The average of these three standardizations showed my nitrite to be 94% pure, which I felt was pretty good given I didn't use a single piece of volumetric glassware anywhere in the entire process. With that, I went ahead and titrated all my samples, making a 6% correction to the calculated percent yields to account for the 6% deviation from my standards. I did end up using 75 milliliters of permanganate solution for each trial instead of the intended 100, as I somewhat overestimated the size of my Erlenmeyer flask. However, I did factor this small edit into my final calculations so that it wouldn't impact the final results. Now, I'm not going to walk through all my calculations because we'd be here all day, but I will post them on screen in case you'd like to see them for yourself. After the 6% adjustment, I found that lead gave a 46.7% conversion of nitrate to nitrite. Iron gave a 36.7% conversion, while zinc gave a 29.3% conversion. Moving on to the nonmetals, calcium sulfite gave a 51% conversion, calcium oxalate gave a 33.4% conversion, iron oxalate gave a 35.2% conversion, and calcium formate gave a 28.7% conversion. None of these numbers were particularly surprising except for the formate and iron oxalate routes, both of which I kind of assumed would be a lot higher. As a final test for this first set of trials, I decided to quickly do a couple qualitative tests. These tests were intended to verify that nitrite was indeed produced, and confirm that the reducing power of these samples wasn't due to some soluble byproduct or unreacted reagent. I considered skipping doing these, but since I had enough of each sample left over from the titrations, I figured it was worth it. For the first qualitative test, I decided to add roughly equal volumes of my nitrite solution to some acidified potassium iodide. Potassium nitrite is able to oxidize iodide to iodine in the presence of acid, which results in a darkening along with the formation of some iodine gas. The degree of observed darkening is roughly proportional to the concentration of nitrite in the sample, and although it's tough to see the differences in the samples from the footage, I tried to arrange the tubes in order of how much iodine was produced. This test strongly supports that all of my samples did in fact contain nitrite, as neither nitrate nor any of the reducing agents I used will have this specific effect on acidified iodide. For a second qualitative test, I did the same thing as before, but this time using copper chloride. Copper forms a unique green complex with nitrite ions while carrying the extra advantage of being very sensitive to impurities. This would allow me to again confirm the presence of nitrite while at the same time detect possible oxalate or carbonate impurities. As you can see, all my samples once again tested positive for nitrite, but the two oxalate samples formed dense precipitates with the copper. This indicates that both of these samples contain significant impurities of what is most likely potassium carbonate, formed as the oxalate decomposed. I again tried to arrange these in order of color intensity, and what surprised me the most is that the formate sample produced one of the strongest colors, despite being the poorest performer in the titration. Now, moving on to my bulk scale trials, I decided to try lead sponge, calcium sulfite, and calcium formate. Zinc was eliminated because it did quite unremarkable at the small scale, and iron was eliminated because I really only wanted to do one metal for my scaled up trials. The oxalates were both eliminated as I really wasn't impressed with their performance and clear impurities in the qualitative tests, given the relative annoyance of having to synthesize these compounds. I kept calcium formate in the running despite its lackluster performance because it seemed to do so well in the second qualitative test that I felt it was promising enough for further testing, and I kept lead and calcium sulfite in because they were the very obvious top performers. To this end, I went ahead and began a 10-time scale redo of the calcium sulfite run. This time I used 40 grams or 0.4 moles of potassium nitrate and 48 grams of calcium sulfite. As a side note, calcium sulfite is not very easy to find given it has very, very limited uses. I made the calcium sulfite I used in this video by reacting calcium chloride with sodium metabisulfite, balancing the pH, and collecting the precipitated calcium sulfite by vacuum filtration. Anyway, I went ahead and mixed together 40 grams of potassium nitrate and 48 grams of calcium sulfite together in a Ziploc bag. I then went ahead and mixed together another 40 grams of potassium nitrate with 83 grams of lead in the same manner and set it aside. The calcium sulfite and potassium nitrate mixture was next transferred to a small steel crucible and heated over my Bunsen burner, only this time for 25 minutes instead of 12. At this larger scale, it was far easier to see that calcium sulfite does indeed have a visible reaction with potassium nitrate that you can see here. The reaction seems to fuse the product salts together along with a slight yellowing and occasional release of toxic nitrogen dioxide gas. After 25 minutes, I went ahead and cut the heat, allowed it to cool, and then soaked it in distilled water to begin dissolving the fused mass. I then went ahead and moved on to my lead sample, which began by dumping my potassium nitrate and lead mixture into a 100 milliliter collection flask that I really wanted to get rid of. This one was also heated for 25 minutes, and the reaction looked about the same as the small scale version, only maybe cooler since there was more to look at. After 25 minutes, I again removed it from the heat and allowed it to cool, which, as expected, destroyed my collection flask. I went ahead and finished breaking it apart so I could transfer the fused salt mass to a beaker where it was soaked in some distilled water to dissolve. Moving on to calcium formate, I decided to do things a little differently this time. Instead of copying the procedure laid out by Experimental Chemistry's video, I decided to begin with 40 grams of potassium nitrate, which was dissolved in a minimal amount of water. To this I added 15 grams of calcium hydroxide and allowed the mixture to stir for a few minutes to get a good suspension of calcium hydroxide. This was then neutralized using formic acid, which was added until all the visible calcium hydroxide had dissolved. Now, the reason I did it this way was mostly to maintain consistency between the runs for this final test. My potassium nitrate is reagent grade, while my calcium nitrate is homemade and thus potentially less pure. Calcium nitrate is also hygroscopic and forms hydrates unlike potassium nitrate, which could add an extra layer of uncertainty to my calculations. Doing it this way, however, eliminates the uncertainty and results in the same solution of calcium formate and potassium nitrate from my earlier trial, and I'm nearly certain the reason Experimental Chemistry used the method he did is because calcium nitrate is the only readily available nitrate salt in the EU. Regardless, once all the calcium hydroxide had dissolved, I went ahead and transferred this mixture to a 1-liter steel beaker thing and put it on high heat. This would first evaporate all the water and then melt the salt so they could react. I did this one in such a huge vessel because the earlier energetic decomposition was a bit alarming, and I was worried it could get out of hand at this scale. As expected, this did eventually result in a very violent reaction that produced a massive volume of gas in a very short period of time. I decided that this was the end of the reaction, so again I took this off the heat, allowed it to cool, and then added distilled water to begin to dissolve my crude potassium nitrite. Now at this point, it was time to clean up my crude mixtures and try and isolate some reasonably pure potassium nitrite. To this end, the first step was the same as with my small-scale trials. Simply wait until the salt masses had completely dissolved, and then filter off each one to try and remove all the insoluble crap. The one caveat here is that the calcium sulfite sample was filtered after I had heated it to nearly boiling, and this was done because calcium sulfate is retrograde soluble, and while virtually insoluble in boiling water, it is soluble enough in room temperature water that enough could get through to cause some annoyance later on. Anyway, once all of the insoluble material was filtered off, the resulting solutions were boiled down to around 75 milliliters, taken off the heat, and allowed to cool. This step is done to remove all of the unreacted potassium nitrate from solution, and this key step is why I chose to make the potassium salt rather than sodium nitrite. Take a look here at the solubilities of the sodium and potassium salts of nitrate and nitrite. As you can see, sodium nitrate has a solubility of 730 grams per liter at 0 degrees Celsius, while sodium nitrite has a solubility of 714 grams per liter at the same temperature. Since these solubilities are so similar, there's really no practical way to separate sodium nitrate and nitrite. And so by making sodium nitrite, you have to accept that you're kinda just stuck with a forever impure product. However, potassium nitrate has a solubility of 133 grams per liter at 0 degrees Celsius, while potassium nitrite has a solubility of 2,800 grams per liter at the same temperature, making it over 21 times as soluble. By significantly reducing the volume of the salt mixture and allowing it to cool, you can thus take advantage of this difference in solubility, as virtually all of the potassium nitrate will crystallize out, leaving you with nearly pure potassium nitrite. To that end, once the solutions had cooled to near freezing, they were each once again filtered, and the resulting filtrate boiled down until only a residue of potassium nitrite remained. These were both further vacuum desiccated and then weighed so I could get their final masses. For the lead reduction, my final mass was 17.52 grams. For the sulfite reduction, my final mass was 21.96 grams, and for my formate reduction, it was 31.07 grams. The theoretical mass for all three is 33.66 grams, but before I started calculating percent yields, I again decided to test each one for its purity. For this second round of titrating, I dissolved 1 gram of each sample along with 1 gram of reagent-grade potassium nitrite into 50 milliliters of distilled water. I then repeated the exact same titration procedure from earlier on each one. The only differences here are that first, I bought a larger Erlenmeyer flask so I could use the intended 100 milliliters of permanganate solution, and the permanganate solution itself was notably stronger this time. I won't go through every aspect of this set of titrations, but I'll post my calculations on screen if you'd like to pause and give them a look. Regardless, after I'd finished my titrations, I calculated that my lead-reduced nitrite had a purity of around 58%, while my sulfite-reduced nitrite had a purity of around 70.2%, and my formate-produced nitrite had a purity of only around 32%. This got me thinking that, potassium nitrite is extremely hygroscopic, and maybe I didn't properly dry my nitrite samples. In order to make absolutely certain that they were completely dry, I loaded them into a toaster oven at 150 degrees Celsius for 3 hours and then weighed them all again. This resulted in the sulfite sample losing 3.8% of its mass, the lead sample losing 4.1% of its mass, and the formate sample losing a shocking 15.3% of its mass. I definitely slacked on drying that one, and I'm guessing it's because I did it weeks later than I did the other two and I was impatient or something. Anyway, I went ahead and repeated the titrations again to get another set of data and hopefully tidy up my results. I used more dilute permanganate this time, and here again are my calculations if you want to give them a look. This time I calculated a 65% purity for my lead-reduced sample, a 79.6% purity for my sulfite-reduced sample, and a 42% purity for my formate-reduced sample. This means that both the lead reduction and the formate reduction worked similarly as well, producing 10.96 grams of potassium nitrite in the case of lead, and 11.34 grams of potassium nitrite in the case of calcium formate. The main difference between the two is their purity, where the lead-reduced sample was over 20% purer than the formate-reduced sample even after the thorough drying step. Calcium sulfite is the standout here, which is funny given it was my original method from over a year ago. This one produced 16.84 grams of pure potassium nitrite at a purity of just under 80%, which is easily pure enough to use for most procedures. Using these final numbers, the true percent yields are 32.55% for the lead reduction, 50.03% for the sulfite reduction, and 33.7% for the calcium formate reduction. I also tried simply heating potassium nitrate to its molten state with no reducing agent for an hour, as I heard that could work. But the result was a 2% yield, which is within my margin of error. I did another set of the qualitative test from earlier, and while that's playing out, I wanted to quickly discuss why I think the purities vary so much in the final samples. As I mentioned earlier, the primary contaminant is potassium nitrate, and while most of that was crystallized out, there is definitely some left hanging around. However, the main byproduct, I think, at this point would actually be potassium hydroxide, which is formed as a byproduct of the reaction. This is because when potassium nitrate is strongly heated, some of it will decompose completely to potassium oxide. This potassium oxide then reacts with water during the dissolution step, forming potassium hydroxide. This makes the final potassium nitrite quite alkaline, and to an extent this is a good thing, as the nitrite ion is stabilized in alkaline conditions, but too much can obviously be undesirable. I assume the reason the sulfite-reduced sample had the least potassium hydroxide impurity is because the reaction took place at a much lower temperature than the lead. Using that same logic, I think the reason the calcium formate-reduced sample contained by far the most potassium hydroxide is because that reaction became an aggressive decomposition when heated, and that increased the temperature far beyond where it should have been, and resulted in much more of the nitrate fully decomposing to nitrogen. Anyway, as I said, the potassium hydroxide contamination isn't really a problem, but if you are truly hell-bent on removing it for a perfect 99.9% pure nitrite salt, I did eventually find a way. With that, if you have some impure sodium or potassium nitrite that you'd like to clean up to near 100% purity, you basically have to selectively precipitate either the nitrite or the hydroxide. This is because both alkaline nitrites and hydroxides have similar solubilities and cannot be selectively crystallized or extracted with any real efficiency. Since comprehensive literature on nitrite salts is somewhat limited, I decided to exhaustively test a variety of metal nitrates to see which one could effectively precipitate either the nitrite or the hydroxide. In the end, period 4 transition metals tended to form soluble complexes with the nitrite before precipitating their hydroxides, which made them pretty useless here. Magnesium nitrate ended up being the only chemical I tested that worked to selectively precipitate the hydroxide. This magnesium hydroxide could be filtered off, leaving a filtrate containing only potassium nitrite and nitrate. I also found that ammonium nitrate can be used in a similar manner, as it'll react with excess potassium hydroxide, forming potassium nitrate and ammonia. This gaseous ammonia can then be removed by heating, again leaving behind potassium nitrate and nitrite. In all of these cases, though, you would need to do one final recrystallization to remove the potassium nitrate, and so precipitation of nitrite rather than hydroxide is easily preferable. Figuring this out took a lot more time than I'm willing to admit, but after a few dozen more rounds of testing, I discovered that silver nitrate, of all things, will react with potassium nitrite to form a virtually insoluble precipitate of silver nitrite. To that end, for a final procedure, I decided to purify some of my lead-reduced potassium nitrite by converting it to pure silver nitrite. To get started on this, I first weighed out 8.7 grams of silver nitrate, which represents about 0.05 moles plus a 0.2 gram excess. Assuming my calculated 65% purity for the impure lead-reduced nitrite was correct, I then weighed out 6.55 grams and began dissolving each of these salts in an arbitrarily small volume of distilled water. As a side note, distilled water is usually not necessary for the vast majority of what you see me do on this channel. However, anytime silver nitrate is involved, distilled water is absolutely necessary, as even small chloride impurities will result in the formation of white silver chloride. This particular salt is so incredibly insoluble that you can see the solution become a bit cloudy even when I'm using distilled water. Regardless, this can be removed by simply filtering the aqueous silver nitrate, and once I felt it was clear enough, I began to slowly add the impure potassium nitrite. This addition immediately began to precipitate the off-white silver nitrite, which was extremely dense and quickly settled to the bottom of the beaker. By doing some basic research, I was able to find that silver nitrite does have a fairly steep solubility curve, being far more soluble in hot water than in cold water. However, even at 60 degrees Celsius, the solubility is still only a mere 13.6 grams per liter, making recrystallization probably more of a headache than it's worth. I also found that silver nitrite will form a soluble complex in the presence of excess nitrite, so it's probably best to use an excess of silver nitrate when making the stuff. Anyway, after the reaction was complete, I simply filtered off my highly pure silver nitrite and allowed it to dry in a cool, dark place overnight. My final yield here was 7.78 grams, representing a virtually 100% of my theoretical, meaning my titrations from earlier were likely quite accurate. This silver nitrite can be used in place of potassium or sodium nitrite in most reactions. In fact, oftentimes silver nitrite can actually be preferable due to its low solubility and the fact that it forms mostly insoluble silver salts as byproducts. As for my final thoughts, I do have a couple quick ideas on how the yields could be further increased from what you saw in this video. First off, I'm really only considering the sulfite process for any future return to this project. This is because the sulfite route was not only the most efficient, but the starting materials are very cheap and accessible at this scale, as well as dramatically safer than using the incredibly toxic lead. That said, I think it's a better usage of time to refine this method that's been proven effective than to try and continue testing increasingly unorthodox methods. To that end, if I was to take another crack at the sulfite method, I think I'd start by using an excess of calcium sulfite and/or heating the mixture at a lower temperature for longer. It might also be interesting to try barium sulfite rather than calcium sulfite, as despite being way more toxic, barium sulfite decomposes at a much lower temperature than calcium sulfite. Not only would this make the lower temperature reduction more feasible, but the resulting barium sulfate is far less soluble than calcium sulfate, which would make purification a good bit easier. To improve the lead reduction, I would suggest using true lead sponge or lead dust. I used very fine lead granules as I didn't want to go through the extra annoying and dangerous process of making lead sponge, but it might be worth the extra effort. The granules worked fine, but they weren't perfectly uniform, and some of the larger pieces didn't really react to completion, given their lower relative surface area. Maximum surface area here is key, and I'd guess you could increase your yield by at least 25% or so by using ultrafine lead. I would just keep in mind that I went out of my way to not do this due to the hazards associated with, ultrafine lead. As for the calcium formate, the really big problem seems to be the explosive decomposition it undergoes at very high heat. I was never able to figure out exactly what temperature this happens at, or if the decomposition is necessary for the reduction to take place. If it's not necessary, which I believe is the case, heating this one a bit more delicately over a much longer period of time could result in at least a much purer final product, if not also much higher yields. Anyway, I hope you found this video interesting, and I hope it wasn't too long. Since I started this channel, my goal had always been to make videos as brief as I possibly could as to not bore anyone. However, I recently heard from many of you that you would prefer longer form content, and to be able to see the whole process of science in action, rather than simply the one final successful result. I do agree it's way more satisfying to finally arrive at a success after numerous failures, but I never figured that would transfer well to video. This is much more the reality of what the scientific process looks like, and if you did enjoy this more honest, realistic, and systematic approach, I'd love to hear about it in the comments. As always, I want to thank all my wonderful patrons for their generous contributions. Your support is vital and very, very appreciated. I'm still waiting to hear back from Patreon on the status of my account, and I'll be sure to update here on YouTube if and when I hear anything. In the case that I can't get the account back, I'm looking at a few other options, including memberships here on YouTube, as well as other platforms similar to Patreon. In the meantime, if you'd like to see more content like this, consider subscribing here on YouTube or following me on TikTok. Thank you all so much for watching, and I'll see you next time.